Chapter 9, Problem 63. A uniform meter stick with a mass of 180 kilograms. So a mass of 100, or sorry, not kilograms, grams. Uniform meter stick, so the mass is distributed evenly everywhere, with a mass of 180 grams, is supported horizontally by two vertical strings, one at the 0 centimeter mark and the other at the 90 centimeter mark. What is the tension A at 0 centimeters and B at 90 centimeters? Okay, so we have a meter stick, and let's say right here is 90. Let's call that 90. So this is 90 centimeters. This is 0 centimeters. And essentially we have something being held. It's being held by strings, and we want to know the tension in the string. So we want to know T1 and T2, right? Both in this spot and in this spot. So how do we go about that? Well, what we can do is look to Newton's second law, and basically we can take advantage of the fact that the meter stick is not moving to help us find some things, right? So the meter stick is in equilibrium, so both the net torque and the net force are 0, and this is very useful for calculating forces and torques. So from our force diagram, we can write an expression for the net torque about this 90 centimeter mark with counterclockwise torques as positive. So let's draw our free body diagram. We didn't really draw a free body diagram of this, or a force diagram, so let's get more technical than this and draw a force diagram. So at this corner, let's call this arrow, where this arrow is acting, let's call this the 0 centimeter mark. So this is tension 1. There's going to be a tension here. We have the meter stick. I'm just going to draw one line now, since we can just imagine it as a line instead of a meter stick. Now, in the center of the meter stick, there's going to be, well, the center of mass is going to be in the middle of the meter stick, right? So this is going to be here. There's going to be a force due to gravity, otherwise known as mg, there. And then we also have another tension, T2, at the 90 centimeter mark. We want to find that. Now we also said that there's going to be a counterclockwise torque around the 90 centimeter mark right here. And essentially that means that any forces going this way are positive, and any going that way are negative, right? So what we want to do next, we can do either the sum of the forces or the sum of the torques. So let's just sum the torques here. So for the sum of the torques on this side, sum of the torques, this is equal to 0, and so is the sum of the forces. But going specifically more into this, let's say that we have the sum of the torques is equal to, well, we're going to have torque 1 minus torque 2 equals 0. But what are torque 1 and torque 2? Well, we have to look at are there any torques anywhere? So if we're calling this our pivot point, this 90 centimeter mark, then we have to use anything with a distance from there. That's basically what's going to be causing a torque. So torque is defined as R cross F. This is in vector signs, or the magnitude is just the magnitude of R cross F, which is equal to R, the magnitude of R times the magnitude of F times sine theta. And so if we have a distance, if we have a force acting at a distance, then, and with an angle in between the force and the distance, then that's where we get our torques from. And so we get this torque here. We have this first distance. The center of mass is going to be at 0.5 actually, right? So this is actually going to be at 0.5. And if it's at 0.5, then 0.9 minus 0.5 gives you 0.4. So it's really acting, the center of mass force is really acting at 0.4 meters, not 0.5 meters. Not exactly half of 0.90, but closer to the middle of the meter stick, right? So the torque one is going to be basically built out of Fg times the distance. It takes the distance to Fg, which is 0.4 meters. It's the same thing for the other force. So we have another distance, another force acting at a distance. This is a full distance, though, from 90 to 0. So this is going to be 90 centimeters. So we're going to subtract the force pushing upwards. We're going to have T1 here times 0.9. And this is all equal to 0. So we know Fg because we know the mass, right? The mass is 0.18 kilograms or 180 grams. You just divide by 1,000 to get kilograms. We know Fg. We have 0.4 and 0.9. I should put a meters there. Just remember to always use units. So this tells us we can find T1, right? T1 is essentially, if we do algebra, we put T1 on the left side here, and we just have to divide 0.9. It's just Fg times 0.4 over 0.9. So with this, you should get 0.78 newtons. So Fg is built out of mg, right? And m is 180 grams. So you can leave it as grams, but if you leave it as grams, then you have to change g into gram form. Make sure you remember that. Otherwise, g is in kilogram meters per second form, which is newtons, basically, like Newton's second law. And that means that you have to use kilograms whenever you're multiplying this 9.80 quantity. Otherwise, you'll get something not so right. If you're using grams, you probably should be using the centimeter version of this, which has a different number here. So be careful about that. I would just stick to using kgs always, if you're using physics. And so this is the answer to A, right? And we can very quickly do the rest of the problem. B, let's open up a new page, and let's just do B. So here we're looking for the tension, right? Yes, did I find it? Oh, may have made a mistake here. Yes, it's not the tension we were looking for, right? Or no, yeah, it is the tension we were looking for. I guess I'm confusing myself calling it this, but the T, these whole things are torques, right? Each of those, and then separately they have the forces. So T is supposed to be a force here, not a torque. I hope that wasn't confusing. So yeah, the force at the 0th, that means this part, right? So the force pushing upwards at the 0 centimeter line is 0.78, and now we can work on the force at the 90th centimeter place. But here we can't use the torque, right? We already used the torque equation, so we have to sum the forces now. If we say the sum of the forces is equal to 0, this is very easy because our force diagram only has up and down. We have no x forces, so we can just say we want to look at the sum of the y forces. This is very simple, right? We only have not F1. We have T1 plus T2 minus mg, right? Because T1 and T2 are above the line, and Fg or mg is below the line. So it's a very simple calculation. With this, we can just find T2, right? Because we know what T1 is, and we've calculated mg as well. So T2 is just simply going to be equal to mg minus T1. This should be about 1.7. This is about equal to, this is not an exact calculation. Make sure you follow through with the full numbers to get the exact answer, but just approximately, this will be 1.7 newtons. This will be also 0.7 newtons, 0.78 newtons. So you should get something about 1 newton, but the exact answer is 0.98. If you use 1.8, if you use 0.18 kilograms and 9.8 meters per second squared and 0.78 newtons, you should get true correct answer for B is 0.98.